In this video, we're going to go through review 1 for all of coordinate geometry. So for number 1, segments AB and CD are perpendicular. If the slope of CD is 5/2, then the slope of AB must be, well, the fact that you need to remember here is that perpendicular lines have negative reciprocal slopes. So what that means is that if one of my segments has a slope of 5/2, the negative reciprocal of that means I need to change the sign. So originally my fraction's positive, my new one's going to be negative, and I need to take the reciprocal. That just means to flip the fraction. So the slope of a line perpendicular to a line that has a slope of 5/2 would be one that has a slope of -2/5. For number 2, which of the following lines passes through the point -4, 5 and is parallel to the line segment whose endpoints are there? Well, first thing you got to remember is that parallel lines have the same slope. Right? Those are two lines that look like that, and they have the same steepness. I could count the slopes for both those. Now, it says it's parallel to a segment that has these endpoints. So the first thing I'm going to do is I'm going to find the slope between those two endpoints. Remember, the slope formula is y2 minus y1 over x2 minus x1. So I'm going to label one of my points as x1, y1, and I'm going to label my other point as x2, y2. And I'm just going to make those substitutions. y2 is 5 minus -3, but remember, if you're subtracting a negative, it becomes positive, and 2 minus my x1 again. It's going to become addition. So 5 plus 3 is 8. 8 divided by 4 is good old 2. So the line that I'm looking for needs to have a slope of 2 because it should have the same slope as the line that passes through those points. So that has a slope of 1/2 and that has a slope of 1/2, so I could rule those out. Remember, all of these equations are in point slope form that looks something like that. Y minus y1 equals my slope times x minus x1, where y1 and x1 just represent the coordinates of any point on my line. And I know one good point that's definitely on my line because it says that my line should pass through -4, 5. So I want you to think about this. If I plug in -4 for this x1 right here, I would get x plus 4 instead of -4 because I would be subtracting a negative. So that's how I can narrow it down between 2 and 3. Number 3, which of the following statements is true about a line that is parallel to the y-axis and passes through the point 5, 8? So just to organize my thoughts here, I'm going to give myself a set of axes. I'm going to sketch about where that point is, and I'm going to highlight the y-axis just so we can look at it. Right, it's just that one up there. So first thing I notice is that to have a line parallel to that, it must look something like this. Now that's a vertical line, and I know those always take the form x equals. So I could rule out those horizontal line equations, y equals 8. So I know that's the equation of x equals 5, because all of the x values on that line are 5. I haven't moved left or right at all. Whether I pick a point down there, or a point all the way up here, I know at least the x-coordinate is going to be 5. The question is, what's the slope? Well, it's just something that it helps to remember that vertical lines don't have slopes. They have slopes that are undefined. And the whole reason that happens is because when I find the slope, change in y over change in x, regardless of what my change in y is, my two x values that I'm going to be subtracting in the denominator there are both 5, because all of my x values are always 5. So what happens is I'm dividing by 0 for my slope, which will always get me an undefined slope. So remember that the lines that have a slope of 0 are those horizontal flat lines that are in the form y equals. Number 4, which of the following is the correct equation describing the linear graph shown? Couple of things. I notice all of these are in slope-intercept form. Remember, that's y equals mx plus b, where m is my slope and b is my y-intercept. Now, if I count the boxes from the origin right there, it looks like that y-intercept is 8, so I could rule out 1 and 3 because those have a y-intercept of 6. And I'm going to count the slope. Remember, slope is defined to be change in y over change in x, or the rise over run. So I'm going to pick two good points that are close together, and I'm going to count. 1, 2, 3, 4. So I went down 4. 1, 2, 3. So I went down 4 and over 3. So my slope is negative 4 over 3. So my best answer choice here has a slope of negative 4/3 and a y-intercept of 8. Number 5. Triangle ABC has vertices with coordinates A, -1, -1, B, 4, 0, and C, 0, 4. Prove that triangle ABC is an isosceles triangle, but not an equilateral triangle, using the distance formula. So remember that an isosceles triangle is going to have two congruent sides, while an equilateral triangle has all three congruent sides. So the reason we need the distance formula here is because that will tell us the length of side AC, if I use it for those points, the length of side AB, and that will tell me which two sides are congruent here and which side isn't. So remember, the distance formula is D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And I'm going to do the distance between A and B first. So if you want to organize yourself, if these are my 2 points, I could label one of them as x1, y1, and I could label my other point as x2, y2 for my second point. When I substitute into the distance formula, so I'm going to find the distance of AB, that's why I put a little AB down there, it's the square root of x2 is 4, minus x1, which is -1, and remember, when you subtract the negative, that's the same thing as adding, squared, plus y2, which is 0, minus y1, which again is -1, so I'm going to add that and square it. Now at this point, I like to plug everything under the radical into my calculator just to see if I get a perfect square or not, to know how to simplify further. And I end up getting radical 26. And 26 isn't a perfect square, and there's no perfect squares to divide into it, so I can't reduce it any further. So that's the length of AB there. I need to do the distance formula 2 more times to find the length of the other sides. So now here I'm going to find the length between B, C by using the same logic, where I label one of my points as x1, y1, and the other point is x2, y2. So x2 minus x1 squared plus y2 minus y1 squared. When I simplify that in my calculator, I get 32 under the radical, and that could break down a little bit. Now I don't have to here, but just as a quick review, if I wanted to break that up, I asked myself, what's the biggest perfect square that divides evenly into 32? Remember, perfect squares are numbers like 4, 9, 16, 25, because that's 2 squared, that's 3 squared, that's 4 squared, that's 5 squared, so it's just a good idea to have those memorized. And if you try a couple in your calculator, you'll find that 16 times 2 is also 32, and radical 16 is just 4. So in simplest radical form, side BC is 4 radical 2. So right now I could see those aren't the same. So those sides are not congruent. So when I solve for side AC using the distance formula, I should get either radical 26 or 4 radical 2, because it tells me to prove that it's an isosceles triangle. So 2 of the sides should be congruent. So I'll find my last side, the distance between A and C here. So I could do x2 minus x1 plus y2 minus y1. And this is all under the radical. Again, when I go into my calculator, I only type in what's under the radical. So 0 plus 1 squared plus 4 plus 1 squared is 26 under the radical. And bingo, that's what we were looking for. That shows that side AC is the same length as side BC. So this is just an application of the distance formula 3 times. So, just as a quick explanation here, we can make an argument that triangle ABC is isosceles because we've shown that side AC is the same as side AB, but triangle ABC is not equilateral because it's not the case that side CB is equal to either of those sides as well. For number 6, which of the following would be the midpoint of segment EF if the endpoints are those right there? Well, I see the word midpoint. I could always plot this and try to eyeball this, but 17 is kind of big to be counting between, so I'm just going to remember the midpoint formula, and that's the average of my x values, comma, the average of my y values. So I'm going to substitute in again. I'm going to add up my x values, divide by 2, and I'm going to add up my y values and divide by 2. Again, I'm a fan of the calculator for these simplifications. You can plug in fractions straight into your calculator. Negative 5 plus 17 is 12, divided by 2 is 6. Negative 1 minus 9 is negative 10, divided by 2 is negative 5. I see answer choice 1, looks like it's the midpoint there. For number 7, segment A prime B prime is the image of segment AB after a reflection across which of the following lines? Well, I'm not even going to look at my answer choices here, and I'm going to try to eyeball where the middle is. It doesn't look like it's a vertical line that it reflected over, because A is not way over here. It looks like it's probably some horizontal line that cuts right through the middle. Notice that point hasn't moved, so that point has to be on the line. And it looks like B is 2 units away there, B prime is 2 units away, A prime is 4 units away, and A is 4 units away, so that line looks pretty good. I know it's a y equals line because it's horizontal, and if I count how far it went up, that's 3 units away from the x-axis. So all the y values on that line are 3. So that's the horizontal line, y equals 3. For number 8, which of the following transformations of segment AB would not result in an image that is parallel to AB, given that AB has endpoints negative 2, negative 3, I'm just going to plot that, and 4, 3. Now I'm plotting this just to give myself an idea of what this would look like, even though I might not need the graph here. A rotation of 180 degrees around the origin. Well, I know rotating 180 degrees by definition should give me something that's just flipped directly around to look like that, so those should be parallel. I could go through all of these. If I reflect over the line y equals x, remember that's this line right there. It goes to the origin, looks something like that. And if I do a quick rule application to those points, remember reflecting over y equals x is just swapping the points, so I'd have negative 3, negative 2, and 3, comma 4. And if I go to plot those, watch what happens. I'm going to erase this in a second. I have negative 3, so left 3, 1, 2, 3, down 2, right there, and 1, 2, 3, 1, 2, 3, 4. Well, looks to me like that's still parallel, so that's not going to help me. And the reason that happens is because AB is already parallel to y equals x. Oh, but watch what happens when I reflect over the x-axis, and you should already be able to see this. If I reflect A just by counting 1, 2, 3, 1, 2, 3, A prime is going to land up there. And if I reflect B, 1, 2, 3, 1, 2, 3, B prime is going to be way down there. And oh my gosh, those intersect. There's no way they could be parallel. So that's going to be the one that keeps them not parallel. And remember, a translation, I could do that even without a coordinate plane. If I translate a segment anywhere, it's always going to remain parallel to the original. So just keep that in mind. For number 9, in the diagram below, rectangle ABCD has vertices whose coordinates are there. Which transformation will not carry the triangle onto itself? So we're looking for something that has no symmetry, essentially. So we're looking for something that's not in the middle. The first thing I'm going to do is I'm going to plot the line y equals x, and I'm going to go through these answer choices. So remember, the line y equals x goes straight through the origin, something like that. And if I fold the rectangle over that line, it looks pretty symmetrical to me. So I'm looking for something that's not symmetrical. If I fold my paper over that line, C would map onto B and D would map onto A. So I'm going to try something else. Reflection over the line negative x plus 10, well, that has a slope of negative 1. That's my slope there. And a y-intercept of 10. So I'm actually going to start at 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to go down 1 over 1, down 1 over 1, down 1 over 1. But when I go to plot this line as well, it's looking to me like it might be another line of symmetry. And look at that, it is. If I fold it over that line, it will land perfectly on top of itself. Now I'm going to try rotating 180 degrees about 6, 6. So let's see where 6, 6 is. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now wait a minute. If I spin it 180 degrees around that point, it's not in the middle of the rectangle. My rectangle is going to end up spun halfway around that point to be on the other side over there. So there's no way that's going to create the same image because it's not in the center of the rectangle. The whole idea why 4 does create the same image is because 5, 5 is right there. It's right in the center of the rectangle. So when I rotate 180 degrees, A is going to line up with C, B is going to line up with D, and so on. For number 9, in a triangle ABCD, BD is the perpendicular bisector of ADC. So I'm going to draw that real quick. Triangle ABC, and BD is the perpendicular bisector. Remember, the perpendicular bisector will do two things. If it's perpendicular, it's going to create congruent right angles. So that means that's going to be a right angle at ADB, and that's going to be a right angle at BDC. It's also going to bisect the segment it intersects. So if it's bisecting a segment, D must be the midpoint of AC, and it must be the case that AD and DC are congruent. So let's go through which one of these must be true. Number 1, BD is a median. Remember, a median just connects a vertex of your triangle to the midpoint of your opposite side. That's exactly what it does because it's a bisector. Also, because it's a bisector, AD and DC are congruent. So that's also true. Let's check this third one out. ADB, angle ADB right there, is congruent to angle CDB. Well, they're both congruent right angles because I have those perpendicular lines, so that is also a true statement. So all three of those statements are true, knowing that it's a perpendicular bisector. So that gives us a lot of information here. For number 10, given segment AB shown below, it's got those endpoints, is rotated 180 degrees clockwise around the origin. So for 180 degrees, because it's halfway around the circle, it does not matter if I go clockwise or if I go counterclockwise. So those both will result in the same image. Remember, the rule for that is it takes a point and sends it to negative x, negative y. So my original point at negative 2, 4, if I apply that rule, again, or you could just turn your paper upside down and plot the same image. If I negate the negative 2, it becomes positive, and if I negate the 4, it becomes negative. Now, B is going to have the same effect, where I'm just going to negate both those endpoints. So I'm going to plot those points just to see what happens, right? So B is going to be at negative 6, negative 1. I'm going to label that as B prime, and A is going to be at 2, negative 4. Remember to always use a straight edge when you connect those, so you could be as accurate as possible when you're describing the relationship between these segments. Now, there's a couple of things you can note for the relationship. Because a rotation is a rigid motion, it must be the case that AB is congruent to A prime B prime. It takes me a while to write it, so I'll just explain in words. A rotation is a rigid motion, and rigid motions preserve distance, so they should be the same length. it's also the case, and you can make this observation as well, that AB should be parallel to A prime B prime, because that's a property of rotations. If I rotate a segment 180 degrees, I'll end up with a segment that's still parallel to the original. For number 11, if the point -6, 4 is rotated 90 degrees about the point 2, 1, then what would the coordinates of its image be? This is going to be one of the trickier ones on here, so I'm just going to start by plotting that. To help myself out, I'll label it as A. And I want to rotate it around 2, 1. That's my center of rotation. 1, 2, up 1. I'm going to call that R for rotation. Now, if you don't remember the process, we don't really have a rule for rotating 90 about a point that's not the origin. So the strategy here is just to pretend that 2, 1 is our origin. And we're going to make some fake points, and we're just going to pretend that this is the origin to help us rotate. So I'm going to create my own, new set of axes around R. So I'm going to make R my origin here. Right? Now I'm going to count from R what the coordinates of A would be. So using 2, 1 as the origin. And I'm just going to organize my thoughts here to see what happens. I go 1, 2, 3, 4, 5, 6, 7, 8 to the left, and 3 up. So this is like my imposter point. A is not really at -8, 3, but I'm just using that to help me apply my rotation rule. Remember that a rotation of 90 degrees takes a point that's x, y, and it bumps and switches it. It bumps the y to the front and switches the sign. So if I apply that from A here, this fake point, I would bump the 3 to the front, change the sign, and the -8 goes to the back. Now again, I'm going to plot this guy from 2, 1. I'm still pretending that R is my origin here. So I'm going to go left 3, 1, 2, 1, 2, 3, and down 8. Make sure you count very carefully. And that's where my image A prime would be. But those aren't the real coordinates of A prime. I use those with reference to R, so they're all defined in relation to my fake origin. So I have the luxury of being able to erase here. You don't, so you just have to count carefully. But I want to count what the real coordinates of A prime there are. And if I count, I go left 1. And if I count down, looks like it's down 7. So as I count from the original origin, the coordinates of that new point is -1, -7. And the good news is, right, you could always check just by going back to 2, 1, that point R right there. I'll make it a little bit darker. I want to show that this is a 90-degree rotation, so watch what I'm going to do. I'm going to connect A prime to R and A to R, and look at what kind of angle that makes. Oh my gosh, it's a right angle. So that could be one way just to mentally check yourself to see if you did it correctly. Number 12, if the point 6, 3, right there, was reflected across the line x = 2, and then reflected across the x-axis, what translation would be needed to move the second image back to the point where it started? Well, I'm going to give myself some labels to make this easier to talk about. So the first thing I'm going to do is sketch where x = 2 is. That means go right 2 units and draw a vertical line where all of my x values are the same. So I'm going to draw it right there. That's x = 2. And to reflect over this line, I'm just going to count the distance from A to the line. 1, 2, 3, 4. 1, 2, 3, 4. So it looks like my A prime is going to be right there. And now I need to reflect across the x-axis right there. So I'm going to do the same process. I'm going to count 1, 2, 3. 1, 2, 3. So A double prime should land right there. So just to organize my thoughts here, I always like to write my coordinates out to help me. A was at 6, 3. If I count carefully, A prime was at negative 2, 3, and A double prime was at negative 2, comma, negative 3. And I want a translation that would move the second image back to where the point started. So I want to slide it back up there, figure out how far right and how far up I need to go. So remember, a translation is just moving either left or right or up or down. So if you count your boxes, if you translate, let's see, this distance right here, if I'm counting carefully, is 1, 2, 3, 4, 5, 6, 7, 8. So if I translate 8 units right, and, that's my symbol for and when I'm lazy, 1, 2, 3, 4, 5, 6, 6 up, and translate 6 units up, I would end up right back where I started. So remember, a translation is just sliding a point across the plane. So this transformation would get me back from A double prime to my original pre-image. Number 13. Trapezoids A, B, C, D, and A prime, B prime, C prime, D prime are graphed, and I want to describe a sequence of transformations that maps this trapezoid onto my new guy here. Well, if you remember the olden days of doing this, we've actually seen this problem before. And it looks like I need to spin it around to get A over there. A reflection wouldn't help me, because it would send A to B double prime over there. So you could actually reflect, but you'd have to do 2 reflections here. There are so many answers for number 13 that I can't go over all of them, but I want to show you the 2 easiest ones that might be easiest to see based on our skills here. It's a rotation to spin it halfway around the circle. But rather than spin it around the origin, if I spin it around 0, 1, and I count, let's see, that goes down 3, right 3, down 3, right 3. A would already land on A double prime, B would already land on B double prime, and all my points would land on each other. So I could actually get this done in one transformation now that I know how to rotate around points that aren't the origin. Or, if you wanted to be careful, you could rotate 180 degrees counterclockwise. I should probably have a direction there too. Rotate 180 degrees counterclockwise around the origin. That could be your first step. And if you apply that transformation to each of them, you should end up with something that gives you A prime there, B prime there. Let's see, 1, 2, 3, 1. C prime there, and D prime there. That's okay too, because all I would need is to translate down 2 units. So I rotate 180 degrees counterclockwise around 0, 0, then translate 2 units down. So that is also fair game. There are so many different ways to do this. If you want to reflect over a horizontal line and then reflect over a vertical line, you can do that as well. So if you have questions about your transformations, please ask in class. Number 14. In isosceles triangle EFG shown, EF and EG are the same. They're both 13. And GF is 10. If a perpendicular bisector was drawn from E to GF, I'm going to do that right now, should be 90-degree angle that it makes with the base there. What would be its length? So really I'm looking for that right there. Well, I see a right triangle here, and maybe I can apply the Pythagorean Theorem that states the sum of the squares of the legs should be equal to the square of the hypotenuse. But the problem is, what is that side down there? Well, it's a bisector as well, so it's cutting GF in half. So it should be 5 on both sides. So really what I have is I have a right triangle with a leg of 5, the other leg I don't know, and the hypotenuse is 13. So I'm going to label that guy as A, that guy as B, that guy as C. It doesn't matter which leg you label as A and B, As long as the hypotenuse is labeled as 13, that's the one directly across from the right angle if you're not sure which one it is. So x squared plus 5 squared equals 13 squared. I'm going to simplify this just a little bit. 5 squared is 25. 13 squared is 169. To undo a plus 25, I'm subtracting 25 on both sides. And remember, to undo a squared, I take a square root. So I get x equals, now I'm happy 144 is a perfect square, so it simplifies just to 12. So that is the height of my triangle, or the length of the perpendicular bisector. For number 15, in triangle DEF shown below, do the following. Plot the image of DEF after a counterclockwise rotation of 90 degrees about the origin. Again, that's negative y comma x. Label its image as D prime, E prime, F prime, and give the coordinates of the vertices below. So it's going to help me, you could turn your paper a quarter turn if you want to. I always think it's easier to have some structure to label my points and then apply the transformation rule that I know. So I draw a little arrow to show where these points are going to go. D prime, if I bump switch, goes to negative 6, 3. E prime, if I bump switch again, goes to negative 6, 9. And if I bump switch for a third and final time, I'm left with negative 2, 3. So I'm going to take a second just to plot those points the best that I can. So let's see, negative 2, 3. It's going to be F prime. Negative 6, 9. It's going to be E prime. And I got a good old D prime right there. Again, you should ask yourself, does it look like this is a 90-degree rotation? Does it look like my original sides are perpendicular to my new sides? And if you're not sure, you could always confirm that. So part B asks me to show that EF and E prime F prime are perpendicular. Now, if they're perpendicular, they intersect at right angles. Now, if I were to extend those, you should try to observe that, hey, it looks like they're going to intersect at right angles, but how do I justify that with coordinate geometry? Well, remember, perpendicular lines, we know something special about their slopes. They have negative reciprocal slopes. So if I can find the slopes between those two segments and show that they're negative reciprocals, that would be enough to show that they're perpendicular. So watch what I'm going to do. I'm going to apply the slope formula. I'm going to find the slope of EF, and I'm going to find the slope of E prime F prime. Now the slope of EF, if I do a quick plug into the slope formula, using these two fellows right here, is going to look like y2 minus y1 over x2 minus x1. 2 minus 6 is negative 4. 3 minus 9 is negative 6. Remember, a negative divided by a negative is positive, and I could divide those both by 2 to get 2 over 3. So you should already be thinking in your head, I want this slope to be the negative reciprocal, which is negative 3/2, because that would show that they're perpendicular. And it says to show that they are perpendicular. So they're telling me exactly what I should get, so my work should justify that. So if I use now E prime and F prime, I'm going to do the same thing for the slope formula. 3 minus 9, y2 minus y1. Negative 2 minus negative 6. Don't ever write that, just make it positive. And I'm going to simplify. 3 minus 9, still negative 6, hasn't changed. And negative 2 plus 6 is 4. You could type this all into your calculator if you want as a fraction, and it will simplify it for you. I just like to show a little bit of work here, but I recommend using your calculator. If I divide those both by 2, I get negative 3/2 as my slope. And lo and behold, that's exactly what we wanted to show. So, if I'm asked to explain my thoughts here, I've talked about it already, but since EF and E prime F prime have negative reciprocal slopes, it must be the case that EF is perpendicular to E prime F prime, which does in fact confirm that I've done a 90-degree rotation here. And again, you could always double check just by connecting one of your points. So I'm going to connect D to my origin where I rotated around. I'll use a fun color here. To D prime and my origin as well. And you should notice, oh hot dog, it's another right angle. So that could be another way for you to check yourself.